If you throw a ball at a wall, it will bounce back. It will do this every time. You would be rightly astonished if the ball suddenly vanished from your side and reappeared on the other, having passed straight through the solid barrier. Yet, in the strange world of quantum mechanics, the set of rules that governs the universe at its smallest scales, this kind of impossible passage is not only allowed, it is happening all the time. This phenomenon, known as quantum tunneling, is precisely the type of behavior that has given quantum physics its reputation for being bizarre and counterintuitive. For decades, this weirdness was believed to be confined to the microscopic single particles. But this year, the Royal Swedish Academy of Sciences has awarded the Nobel Prize in Physics to 3 scientists who demonstrated that these bizarre rules are not just for the very small. John Clarke, Michel H. Devoret, and John M. Martinis will share the 2025 prize for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Working together at the University of California, Berkeley, in the mid-1980s, the trio built an electrical circuit, a device large enough to be held in the hand, and proved that it could behave as a single, unified quantum object. This tiny chip, containing billions upon billions of particles, could collectively perform the impossible feat of tunneling through an energy barrier. They also showed that this large system, like a single atom, could only absorb energy in discrete, measured packets. Their work provided a stunning answer to a question that had lingered since the birth of quantum theory. Do the strange laws of the subatomic world apply to larger objects? Or do they somehow fade away as things get bigger? They showed that the line between the quantum world and our everyday world isn't set in stone. In fact, you can actually move that line back with some clever and careful engineering. What they achieved wasn't just seeing a quantum effect in a new place, but really showing off a whole new level of control over the quantum world. They engineered a system to produce and measure a fragile quantum state, isolating it from the noisy clamor of the ordinary world. This act of control was the conceptual starting point for the entire field of quantum technology, including the quantum computers being built today. The idea of quantum tunneling emerged shortly after the development of quantum mechanics in the 1920s. The new theory replaced the old, common-sense picture of a particle as a tiny billiard ball with a specific location. Instead, it described a particle with a wave function, a mathematical object that represents a cloud of probability. The wave function tells you the likelihood of finding the particle at any given point. For the most part, this cloud is concentrated where you would expect the particle to be, but the edges of the cloud can be surprisingly far-reaching. If a particle approaches an energy barrier, a hill it does not have enough energy to climb, most of its probability wave will be reflected. But a tiny, faint part of the wave can leak through the barrier. This means there is a small, but not zero, probability that the particle can simply appear on the other side, as if it had tunneled through the hill. This was not just a mathematical quirk. In 1928, the physicist George Gamow realized that tunneling was the explanation for a long-standing mystery, the radioactive decay of certain atoms. The forces within a heavy atomic nucleus create an energy barrier that should, by all classical accounts, permanently trap the particles inside. Yet these nuclei decay, spitting out a small piece known as an alpha particle. Gamow showed that the alpha particle was not breaking out of its nuclear prison, but tunneling out. Tunneling explained why radioactivity is a probabilistic process. For any single atom, it is impossible to predict when it will decay. One can only state the probability, often expressed as a half-life, the time it takes for half of a large sample to decay. An even more elemental example of tunneling powers our world. The core of the sun, while incredibly hot, is not quite hot enough for hydrogen nuclei, which are single protons, to overcome their powerful electrical repulsion and get close enough to fuse. According to classical physics, the sun should not be able to ignite. The sun shines because quantum tunneling allows two protons to breach that repulsive barrier and merge, releasing a tremendous amount of energy. The light and warmth that make life on Earth possible are a direct consequence of this quantum ghostliness. Tunneling, as you can guess, is a fundamental process of the cosmos, driving both the decay of matter and the creation of starlight. It redefines what is possible in the universe. Classical physics deals in certainties based on energy. If a particle lacks the energy to cross a barrier, it cannot. Quantum mechanics replaces this absolute restriction with a game of chance. This probabilistic nature of reality allows for events that would otherwise be forbidden. The laureates' great achievement was to take this wild cosmic process and domesticate it, harnessing it inside a device of their own making. To build a macroscopic object that could tunnel, the Berkeley team needed a very special material, a superconductor. In an ordinary electrical wire, current is a chaotic flow of individual electrons that jostle against the atoms of the wire, losing energy and generating heat. This is the basis of electrical resistance. But when certain metals are cooled to temperatures just a few degrees above absolute zero, something remarkable happens. Their electrical resistance vanishes completely. They become superconductors. The theory explaining this was developed in 1957 by John Bardeen, Leon Cooper, and Robert Schrieffer. It revealed a strange and beautiful choreography taking place within the metal. According to their BCS theory, as it is known, the electrons in a superconductor stop acting as individuals and form pairs, called Cooper pairs. The pairing is indirect, as one electron moves through the grid of positively charged atoms that form the metal's structure. It slightly distorts the grid, creating a fleeting region of concentrated positive charge. This positive region then attracts a second electron, binding the two together over a relatively long distance. This pairing has a big impact. Individual electrons are a type of particle known as a fermion, which are fiercely antisocial. The rules of quantum mechanics forbid any two fermions from occupying the exact same quantum state. Cooper pairs, however, behave as a different kind of particle called a boson. Bosons are gregarious. Any number of them can happily occupy the same quantum state. This allows for a collective phenomenon on a massive scale. All of the billions of Cooper pairs within a piece of superconductor can condense into a single, shared quantum state. They begin to move in perfect unison, like a vast synchronized dance. They can be described by a single macroscopic wave function, as if they were no longer a collection of particles, but one giant quantum entity. This collective quantum state is the stage for the Nobel-winning experiments. But to access it, the researchers needed one more component, a device that acts as a gateway to this macroscopic quantum world. That device is the Josephson junction. Predicted by the British physicist Brian Josephson in 1962, It consists of two superconductors separated by a very thin layer of insulating material. Josephson calculated that Cooper pairs could tunnel across this insulating gap without any resistance, creating a supercurrent. The Josephson junction is the critical element because its electrical behavior is directly linked to the quantum state of the superconductors on either side. It acts as a kind of transducer, converting the hidden, ghostly properties of the macroscopic quantum state into familiar, measurable quantities like voltage and current. It is the bridge that allows an experimenter in our world to talk to the quantum world. The physics describing the behavior of a Josephson junction is complex. In simple terms, the collective quantum state of all the Cooper pairs in the circuit can be mathematically described as if it were a single fictitious particle. The position of this imaginary particle does not correspond to a location in space. Instead, it represents a purely quantum property called the phase difference between the two superconductors on either side of the junction. This fictitious particle exists in a peculiar landscape, a potential energy surface often called a tilted washboard potential. One can picture it as a marble rolling on a sloped, corrugated ramp. The corrugations create a series of valleys, or wells, where the marble can become temporarily trapped. This picture connects directly to the real-world experiment. When the fictitious particle is trapped in one of the wells, the Josephson junction is in what is called the zero-voltage state. No voltage appears across it. If the particle manages to escape the well, it will begin to roll freely down the tilted ramp. This running state corresponds to a sudden appearance of a measurable voltage across the junction. The central question is, how does the particle escape from its well? There are two possibilities. It could be shaken out by thermal energy. At any temperature above absolute zero, the system has some heat, which causes the particle to jiggle. A sufficiently violent jiggle could knock it over the wall of its valley. This is the classical explanation. The other possibility is that the particle could tunnel directly through the wall of the potential well. This would be a purely quantum escape. The goal of the Berkeley experiments was to determine which of these two processes was at play, to find out if their fictitious particle, which represented the collective state of billions of electrons, truly obeyed the laws of quantum mechanics. And what made their experiment so powerful was that this quantum landscape was not fixed. The laureates could alter its shape at will. The equation for the washboard potential depends on the amount of electrical current being sent through the junction. By carefully adjusting this bias current, they could change the tilt of the washboard, making the walls of the valleys higher or lower. This ability to sculpt the potential landscape gave them an unprecedented level of control, allowing them to not just observe the quantum system, but to actively probe it. In the mid-1980s, the team at the University of California, Berkeley took up the challenge. The group was led by John Clarke, a professor specializing in superconductors. He was joined by Michel Devoret, a postdoctoral researcher from France, and John Martinis, a doctoral student. Their work was inspired by the theoretical physicist Anthony Leggett, who had suggested that observing macroscopic quantum tunneling might be possible in superconducting circuits, and had worked out how such a system would be affected by its environment. The technical hurdles were immense. The main adversary was noise. Any stray heat or electromagnetic radiation from the environment could give the fictitious particle a classical thermal kick, shaking it out of its potential well. This thermal escape could easily mimic or completely overwhelm the subtle quantum tunneling effect they were looking for. To succeed, they had to create one of the quietest and coldest places on Earth. Their experiment was housed inside a dilution refrigerator, a machine capable of reaching temperatures of just a few thousandths of a degree above absolute zero. They designed elaborate filtering systems for all the electrical wiring running into the experiment, using things like tightly packed copper powder to absorb any stray high-frequency radiation. Their first experiment was designed to find the telltale signature of quantum tunneling. The method was conceptually simple. They would slowly increase the bias current, which tilted the washboard potential and lowered the wall of the well. They would record the exact current at which a voltage suddenly appeared, signaling that the particle had escaped. They repeated this measurement thousands of times to build up a statistical distribution of escape events. They performed this procedure at different temperatures. At higher temperatures, the escape was clearly driven by thermal energy. As they cooled the system down, the particle needed less of a thermal jiggle to get out, so the average escape current increased. But then, as they reached the lowest temperatures, something crucial happened. The escape rate stopped changing. It flattened out, becoming independent of temperature. This was the smoking gun. The particle was no longer being shaken out by heat. It was escaping on its own, through the quantum mechanical process of tunneling. This was a remarkably clear observation of microscopic quantum tunneling. The team then performed a second, even more elegant experiment that provided definitive proof. They reasoned that if their macroscopic system were truly a quantum object, it should not be able to possess any arbitrary amount of energy. Like an atom, its energy should be quantized, restricted to a series of discrete levels or steps. To test this, they irradiated their Josephson junction with microwaves. The idea was that the system would only absorb a microwave photon if its energy precisely matched the gap between two of its quantized energy levels. When the system absorbed a photon, the fictitious particle would be promoted to a higher energy level. From this higher perch, the wall of the potential well looks lower and thinner, making it much easier for the particle to tunnel out. This effect is called resonant activation. By sweeping the frequency of the microwaves and monitoring the escape rate from the well, the team could perform spectroscopy on their macroscopic object. When the microwave frequency hit a resonance, matching an energy gap, the escape rate would spike upwards. Their data showed a series of sharp, distinct peaks. It was a direct map of the quantized energy levels of their artificial atom. The two experiments provided a powerful interlocking case. The first showed that the system exhibited quantum behavior by tunneling. The second showed that it had a quantum structure of discrete energy levels. This combined evidence was irrefutable. Clarke, Devoret, and Martinis had successfully performed atomic physics on an electrical circuit they had built themselves. The conclusion from the Berkeley experiments was clear and startling. A macroscopic object, designed and fabricated in a laboratory, could be engineered to behave as a single, coherent quantum mechanical entity. This finding directly addressed one of physics' most perplexing mysteries, often exemplified by the Schrödinger's cat thought experiment. In 1935, Erwin Schrödinger, one of the founders of quantum theory, imagined a cat in a sealed box whose life or death was tied to the decay of a single radioactive atom. According to a literal interpretation of quantum mechanics, until the box is opened, the atom is in a superposition of both decayed and not decayed, meaning the cat must be in a superposition of being both alive and dead. Schrödinger intended this to show the absurdity of applying quantum rules to large objects like cats. The laureates experiment did not create a cat that was simultaneously living and dead, but it did create a system of billions of Cooper pairs that were collectively in a quantum superposition of two different states, corresponding to the particle being trapped in its well. It was what Anthony Leggett called a laboratory cousin of Schrödinger's cat. The experiment showed that there is no magical size at which quantum mechanics simply stops working. The boundary between the quantum and classical worlds is not a fundamental law of nature, but a technological challenge. With sufficient isolation and control, large things can be made to act quantumly. Out of this work grew a powerful new concept, the artificial atom. Like a natural atom, the Berkeley circuit had a ladder of discrete energy levels. It could absorb and emit single photons of energy. But unlike a natural atom, it was entirely man-made. Its properties were not dictated by nature, but were set by the design of its capacitors and junctions. You could connect wires to it and measure it with standard laboratory equipment. This was the birth of a new kind of quantum hardware. The Nobel Committee's decision to recognize this work now, 4 decades after it was performed, reflects its foundational importance. The demonstration that one could build and control a macroscopic quantum system was the essential first step. It showed that the dream of building complex machines that operate on quantum principles was not a fantasy. The experiments of Clarke, Devoret, and Martinis laid the groundwork for the entire field of superconducting quantum computing, which is now one of the most promising avenues toward building a powerful quantum computer. Their work represents a turning point in our relationship with the quantum world. Before, quantum mechanics was a theory used to describe the world as we found it. After their work, it also became a set of design principles for building a new artificial world of our own creation. The direct legacy of the Berkeley experiments is the quantum bit, or qubit, the fundamental unit of information in a quantum computer. The 2 lowest quantized energy levels that Clarke, Devoret, and Martinis measured in their artificial atom can be used to represent the 0 and 1 of a qubit. The ability to exist in a superposition of these 2 states is what gives a quantum computer its potential power. In the years that followed, researchers built on this foundation, developing an array of different superconducting qubit designs. One of the laureates, John Martinis, went on to pioneer a design known as the phase qubit. Other groups developed charge qubits. These early devices were proof that quantum computation with circuits was possible, but they were extremely sensitive to environmental noise and could only maintain their quantum states for very short times. Experience with these first-generation qubits revealed the primary culprit, something called charge noise, which caused the energy levels to fluctuate and destroyed the quantum information. This led to a major breakthrough in 2007 with the invention of the transmon qubit, a design cleverly engineered to be much less sensitive to charge noise. One of the key figures behind the transmon was another of this year's laureates, Michel Devoret, working with colleagues at Yale University. The transmon is now the workhorse design used in many of the world's most advanced quantum processors, including those built by Google and IBM. At the same time, Devoret and his Yale colleagues Robert Schoelkopf and Stephen Girvin developed a new architecture for controlling and reading out these qubits, known as circuit quantum electrodynamics, or CQED. This approach uses microwave photons as a quantum bus to carry information between qubits housed in a superconducting chip, a critical step toward building a full-scale processor. The path from the foundational experiment to a powerful technology is becoming clearer. John Martini, after pioneering the first qubits, went on to lead the team at Google that, in 2019, used a 53-qubit processor based on transmons to perform a calculation that would be effectively impossible for even the largest classical supercomputers, a milestone known as quantum supremacy. The 2025 Nobel Prize in Physics really shows how science moves forward. It all started with a question of, can a big object act like it's quantum? Answering that took some seriously amazing experimental work and clever thinking, and what they learned from that basic research didn't just give them an answer, it created a whole new foundation, the artificial atom, which became super important for a brand new area of technology. The Nobel Prize is being awarded now because the technological flywheel that Clarke, Devoret, and Martinis first set in motion in 1985 is now spinning fast enough for its world-altering potential to be available to all.